Ever wonder what's really going on deep inside your computer? Not just the code, but the fundamental rules that govern everything it does? Well, today we're going on a journey to explore exactly that. We're going to climb what I like to call a ladder of power to understand not only what makes computers so powerful, but also to discover their absolute unbreakable limits. But you know what? Let's just jump right to the big one, shall we? The one question that drives this whole thing. Are there problems out there that a computer, any computer, even a supercomputer from the future can simply never solve? Just hang on to that question, because the answer, I promise you, is going to change the way you think about everything. All right, so before we can even begin to talk about the limits of computing, we kind of have to take a step back. We first have to agree on what computation even is. And believe me, that is a much bigger and cooler question than it sounds. Now, we're not talking about learning to code in Python or building a faster gaming PC here. This is way more fundamental. The theory of computation is all about creating these abstract, almost imaginary models of machines. And what's so wild is that by understanding these super simple models, we can actually grasp the core abilities of every single computer that has ever existed or ever will. Okay, so let's get started. We're going to step onto the very first rung of our ladder of power. It's time to meet this simplest, most basic model of a computer you can possibly imagine. It's called a finite automaton. Yeah, I know it sounds a little bit intimidating, but the idea is dead simple. Think of it as a machine that can only be in a few different states, and its only job is to recognize really simple patterns. But here's the absolute most crucial part. It has zero memory. None. It has no idea what happened a second ago. All it knows is the state it's in right now. And you actually use these things every single day. A vending machine? It's a perfect real-world example of a finite automaton, right? It starts in one state, waiting for money. You put in a coin, click, it changes to a new state, has money. You press the button for your selection, clunk, it moves to the dispensing item state. It's just following a simple fixed set of rules, and it has no memory of the person who used it 5 minutes before you. And this shows you exactly what it's good for, and what it's completely useless for. It's great for simple jobs, like checking if your password contains a number, or running a traffic light. But ask it to do something like check for balanced parentheses in a line of code. Making sure every opening parenthesis has a matching closing one? Nope, can't do it. And why not? Well, think about it. To know if a closing parenthesis is valid, you have to remember seeing the opening one, right? This little machine can't remember. It can't count. And that is its big, fatal flaw. So how do we fix that? Well, it's pretty straightforward. We climb up to the next rung on the ladder. It's time we give our machine a way to remember. And really, that's the whole ballgame. That one missing ingredient, memory, is what separates a simple on-off switch from something that can actually compute. So, say hello to our next model, the push-down automaton. It's basically our first machine, but with a cool new upgrade, a superpower, really. It has access to a simple type of memory called a stack. Now, this stack memory works in a very particular way. Just picture one of those plate dispensers you see in a cafeteria, the spring-loaded kind. You can only put a new plate on the top, and you can only take the top plate off. The last plate you put in is always the first one you take out. We call this last in, first out, or LIFO. It sounds almost too simple, but believe me, this one little addition changes everything. Because with this stack, our machine can now totally crush that parentheses problem. Every time it sees an opening parenthesis, boop, it pushes a little token onto its stack. Every time it sees a closing one, bip, it pops one off. If it gets to the very end and the stack is empty, boom, the parentheses are balanced. And just like that, a whole new universe of problems just became solvable. Okay, so we've added memory, which is a huge step up, but it's still pretty limited. So now it's time. Time to climb to the final rung on our ladder, to the theoretical model that defines all modern computing. This is it. The Turing machine, conceived by the absolute genius Alan Turing. The idea is so elegant. Just imagine a little machine with a head that can read and write symbols on a tape that is infinitely long. That infinite tape is the secret sauce. It represents unlimited memory. The machine can just move back and forth, reading, writing, and changing its state based on a set of rules. It can remember anything it wants. And this simple concept leads to one of the most powerful and, frankly, mind-blowing ideas in all of science, the Church-Turing hypothesis. What it basically says is that if a problem can be solved using a step-by-step procedure, what we call an algorithm, then a Turing machine can solve it. Full stop. It is the universal computer. And please don't think this is just some dusty old abstract theory. This is real. The device you're watching this on right now, your laptop, your phone, it's just a physical, real-world version of a Turing machine. Sure, its memory isn't literally infinite, but in practice, it's the same principle. This simple model is the very soul of everything your computer can do. So, here we are. We've made it to the top. We have the all-powerful Turing machine with its unlimited memory. It feels like we've found the ultimate problem-solving tool. But do you remember that question I asked you at the very beginning? Is this machine truly unstoppable? Can it solve every single problem we can possibly throw at it? Well, amazingly, it was Alan Turing himself who discovered the machine's Achilles heel. It's a famous puzzle known as the halting problem. The question sounds simple enough. Could you write one master program that could look at any other program and its input and tell you for sure, with a simple yes or no, whether that program will eventually finish its job or get stuck in an infinite loop and run forever? And the mathematically proven answer is a massive, earth-shattering no. It's not just that we haven't figured out how to write that program yet. It has been proven with the certainty of a math equation that such a program can never exist. And that's it. That's the answer we've been looking for. We finally found it, a hard, defined limit to computation. There are problems out there, like the halting problem, that are fundamentally undecidable. No computer, no matter how powerful, no matter how much time you give it, can ever be built to solve them. And that brings us right back to where we started. We now know that yes, there are problems a computer can never solve. But this discovery does more than just define the limits of our machines. It forces us to think about the nature of problems, of logic, of knowledge itself. Because if even a perfect theoretical computer with infinite power has these unbreakable walls, what does that suggest about the limits of our own understanding?